final day session on shear flow transition and turbulence. It's my pleasure to introduce the first speaker, Javier Burguete from Pamplona, who's going to talk about slow temporal scales and dynamics of vortices at large Reynolds numbers in a cylindrical container.
Thank you very much, Professor Moulin. Good morning, ladies and gentlemen, and thank you for being here in this early talk in the morning. I'm going to talk about the dynamics of these vortices that appear in a von Karman flow when the Reynolds number is very large. Very large means for me something like 10 to the 5. And this is a work that has been done here in the University of Navarra in Pamplona in Spain. It's a small city in the north part of Spain. This is the people involved in this project. Most of the results that I'm going to present are part of the PhD thesis of Alberto de la Torre. Well, then the first question arises why to study the slow scales in this kind of dynamics? Well, there are two reasons. The first one is because of fundamental reasons. There are many open questions about how the mean flow suffers different transitions in a fully developed turbulent regime, and also what's the role of the coherent structures on these dynamics. But also because I am interested in the original interest, or the origin of this experiment was the dynamo action. This is a flow that is candidate to produce a dynamo action. Then the question was how the slow scales can affect the position of the threshold of the dynamo action. Well, yesterday we had a very nice talk by François Davio about a very similar experimental setup. Then let me recall only 2 points. The vortices has been observed in the fully developed turbulent regime in experiments in Saclay. For example, this is a picture taken from the thesis of Louis Marié. And you may find a lot of information about the transition to the turbulent regime here in this reference, but also in the numerical simulation, these vortices has been observed in the equator of a cylinder, where the top and bottom plates rotate in opposite directions. And here are some references about the numerical simulation, and here there are some experiments at low Reynolds. Well, this is our experimental setup. Our experimental volume consists in a cylinder that is placed horizontally, and there are two impellers here at both ends of the cylinder that will rotate in opposite directions. And the impellers have 10 blades that are 2 centimeters high. The height and the diameter of the cylinder is the same, 20 centimeters, so the aspect ratio is 1. And the cylinder is placed in a tank of 200 liters of water. You may ask why blades are not flat disk. This is a question that the people that are working with numerics ask a lot. But there are two reasons. The first reason is because we wanted to inject as much kinetic energy in the volume as possible, and the blades are much more efficient than flat disk. But the second one is much more interesting. The second reason is a physical reason, because the impeller design allows to modify the ratio between the azimuthal to meridional components of the velocity field. Then this is called the poloidal to toroidal ratio. The critical point is the angle between the blade and the propeller's rim, or the border of the propeller. Then in this way we can change this ratio, the ratio between the azimuthal and meridional velocities, and so we can control in some way how is the shear layer here in the middle of the system. Well, I'm going to show you a picture, a video. I hope it works. Here we will see the flow that appears with a Reynolds number of 10 to the 5, more or less. Okay. There are some points that should be noted here. The first one is that the vortices are not stationary. They are going upwards. I don't know if you can see very well. The vortices are here and not moving in this direction. but they are not located in the equator. The equator is something by here. Here, in this Reynolds number, the vortices are displaced towards this impeller. This impeller is turning in this direction. The other impeller is rotating in the other direction. So the vortices are following this impeller. And this is something that we found. There are two solutions. Or the vortices are moving upwards, then following this impeller, and the position is displaced in this direction. Or the other possibility is that the vortices move downwards, following this impeller, and then the shear layer is displaced in this direction. And this is something that is recovered in the average velocity field and the mean velocity field. Here you can see this is the meridional component, and this is the azimuthal component of this gray region. Then the impellers are here, and here, here, and here, and this is the axis of the system. And then you can see that the shear layer that is located here is not in the equator, but is displaced something like 20 millimeters in this configuration. And this corresponds to the position of the vortices. Then there are two mirror possibilities. We have this solution of the other one. This is what we call the south state, because for historical reasons we call this the north. The north state, because for historical reasons we call this propeller the north, and this is the south propeller. Okay. Then you may ask that this asymmetry is produced because of experimental asymmetries, but this is not the case. The experiment is as good as possible. For example, the propellers, the velocity of the propellers is the fluctuations are less than 1 part in 10,000. That is quite good, I think. Then, but anyway, we wanted to test what is the effect of an asymmetry introducing an asymmetry in the system. Then we define this delta. In the yesterday talk, Juan Sadovio called this parameter theta, but for me, theta is the azimuthal component, and then there is a small problem. Then I will call delta the asymmetry between the velocity, the frequencies of both propellers. Then if the symmetric solution was available in this problem, what we should expect to recover here is something like that. When delta goes to 0, this is the position of the shear layer, sorry. Then as delta goes to 0, we will recover a symmetrical velocity field. But in this configuration, what we obtain is that there are two branches, and they converge to these points. And then for delta equal to 0, we have a B stability. If we record a very long temporal series, very long means something like here we have 2 hours and a half, but we have a record of 17 hours. That is very long for this system. Please remember that the propellers are rotating with a frequency of 8 hertz. Then we can see here, this is the velocity of a point located in the equator. We can see here that the system remains in the south state. Then there is a jump to the north state, south state, north state, south, north, south, north, south, and so on. Okay, and you can see that the residence time is not constant, but there is some kind of random behavior. And here the velocity is fluctuating around a mean value with a turbulent rate that is 100%. Well, then how does this behavior appear in the system? Here I present the PDF of the velocity in the equator for different Reynolds numbers. For a low Reynolds number, something like 10 to the 4, the system has a PDF that is symmetric, is Gaussian, is located at the position of 0 velocity. That means that the system is symmetric, the shear layer is placed in the equator. But when we increase the Reynolds number, the PDF becomes wider and wider, and two maxima appear here in the system. This PDF, plotted in green, correspond to this data series. Okay. Then why there is this M shape in the system? Well, we can separate the south and north state applying a low-pass filter, and we can compute the PDF of each state separately. And then what we recover is that each PDF, each state has a different PDF. Then there are fluctuations around covering this range of velocities for the south state and this range of velocity for the north state. If we combine this PDF, we will recover the M shape that I showed before. Well, but even more, then there is here a time scale that is a characteristical time scale that is something like 500 seconds or something like that, that governs this alternation between the north and south states. But if we zoom in the behavior of the north state, for example, this plot is for 50 seconds. 50 seconds in this time scale means more or less the width of this number 1. Then is really a big zoom. What we can see is that the fluctuation of the velocity in the north state is, and also in the south state, of course, is not something really random around a mean value, but there are two accumulation points here near 0, near a negative value, 0, negative, and so on. We can do again the same treatment. We can apply a low-pass filter and recover the PDF for each state. And then now each one of these states has a Gaussian profile. If we combine these Gaussian profiles, we recover the shape of the north state, and then we can see that the original M shape that we have in our system is the result of combining 3 different Gaussian oscillations around 3 fixed points. Okay, we can calculate here the amplitudes of these Gaussians. And here is the power spectra of the system, of the very long data series with a lot of inversions. Here we can see that there are some time scales. This is the time scale for the characteristical time scale for the inversions. This is the characteristical time scale for the small the alternation that appear in the slow and in the 15 seconds range between the 0 velocity and negative velocity. And this is the velocity of the vortex when that is rotating in the cylinder. This is the Kolmogorov slope. This slope can be explained because of the inversions between the north and south state, but we don't know. There is no explanation about why this slope appears in the system. Okay. Well, I was saying that we can compute the amplitudes of the Gaussians, and here's what is plotted here is the amplitude of the central Gaussian as a function of the Reynolds number, and also the amplitude of the north and south Gaussian. And then here you can see that there is a clear bifurcation for a Reynolds number of 10 to the 4. There is a symmetric a PDF that is centered around 0. But when we increase the Reynolds number, this amplitude increases, and then here we have 3 fixed points that are available for the dynamics of the system. Then what is amazing here is that most of the characteristics of this flow can be recovered using a very simple model, a dynamical model, a toy model without the spatial component. This is we have 3 fixed points. Then the one idea was to test compare the evolution of our system, our turbulent system, with a 3-well potential. That means a 6-order polynomial here for the potential. The turbulence has been replaced by a white noise. Here this term takes account for the asymmetry of the system. Then we can change the depth, the relative depth of each one of the walls. Using this method, this model, we can recover, for example, the PDF of the escape times. The crosses are the experimental data. The dotted line is the simulation. These are the PDF of each state. Well, it's not more or less. And this is the amplitude of the behavior of the amplitudes in the model. Well, but there was a problem. This model predicts that should be an hysteresis window in the system that we didn't observe. Then we looked for this hysteresis, and we found that in the experiment, really, there is a very small hysteresis window. For example, for this value of delta, the south state is favorized, is much deeper, this well than this other, and then the residence time here is longer. For the negative value, we recover the opposite situation. We can compute the escape times for these states. We can calculate the slope. This is the escape time for the south and north states. And thank you. And then if here what is plotted is that the slope of the escape time as a function of delta, when there is no hysteresis, this value diverges to infinite. And then we can see here that there is a small hysteresis window of something like 1% of delta. Well, this is the main results. We can force also the system. For example, we can apply a sinusoidal forcing with a sinusoidal, we can change the velocity using this function. And the system follows the forcing up to a frequency of 0.1 hertz. Okay, if we increase the frequency further from this value, there is no effect of the forcing in the system. But something that for me is more interesting is that if we apply a random forcing, it's a quite peculiar random, because we wanted to test the effect of the time scales included in the random function. The idea is to limit how fast the forcing can evolve, because we wanted to test how the different time scales are destroyed. We can see that there is a strong correlation between the noise, the forcing, and the signal up to a time of 10 seconds. The long temporal scale has been destroyed. There are no residence time of something like 1,000 seconds. If we reduce this tau, the correlation is lost, and we can recover, for example, a symmetric PDF for very short periods of time. And this is the summary of the forcing. These are the conclusions. Then in this system we can see that we can obtain something like very rich dynamics that can be recovered, that can be explained using a very simple model with potential, with a very simple potential. We can have a random inversion periodic behavior, or we can force a stationary non-symmetric flow. Also, we have identified here different temporal scales. Of course, this is clear, but we have no idea about why this temporal scale or this temporal scale appear in the system. And that's all. That's something that I would like to show about the ubiquitous of vortices in the nature. Thank you very much.
How sensitive is this asymmetric flow to details of the impellers or the apparatus in general?
Sorry, could you repeat?
So you get this, but how sensitive is it to change the impellers? I think Javier said different impellers gave less.
Yeah, we have tested different impellers, and also we have changed the velocity of the impellers. If we change the impellers, you will obtain a different behavior. You may obtain, for example, a symmetrical velocity field that remains for very large Reynolds number, or you may find, for example, something that François Javier showed yesterday, that you may have a transition from a two-cellular flow to one big cell in the system. Then the dynamics is really depending on the shape of the impeller. But the shape of the impeller controls the ratio between the different components of the mean velocity field. And that's the parameter here, how the shear layer.
In the VKS experiment, they also have a ring around the equatorial plane.
Yes.
That's important for dynamo action. Have you tried that?
No, I've been talking with François Javier. He's not here, but okay. And then they have tried to obtain the velocity field with and without annulus. I think that there is a preprint of a paper in Archive now that has been sent by the group of Saclay, in July. And they showed that the effect of the annulus is to the shear layer is anchored to the equator, but in this situation there are still vortices that appear, but now instead of one vortice, they have something like a pair of vortices that are rotating around the annulus. Yes.
Final question.
What's the lowest Reynolds number that you've studied?
10 to the 4.
10 to the 4, so 10,000.
Well, yes, because we need to change the fluid in order to decrease the Reynolds number that is available in our system.